All right, welcome back, everybody. So today I want to bring together a couple of the themes that we've been talking about recently, right? We spent a few lectures talking about, that seems a little louder than normal, I'll go with it. We spent a few lectures talking about control. We talked about manipulator control. And then we spent a little bit of talking about deep perception. Okay, and I want to start by sort of starting to bring those threads together, and that's kind of the theme of the lecture today. Okay. So in the manipulator control world, we had some beautiful equations, right? We had our multi-body equations. Lots of structure. We learned how to write really good controllers for them. Okay. In particular, we figured out how to do trajectory tracking. So if you gave me Q of t, if it was differentiable twice, I could write a really good controller to try to track Q of t with high accuracy. The more I knew about the model, the more the higher performance tracking I could get. We talked about force control, both indirect and direct. So I could actually control the force or the impedance that I was putting at a certain point on the manipulator and just control the interactions I was having with the world. Okay, but what's really important to make sure you understand is that all of that was about controlling the robot degrees of freedom. Degrees of freedom, right? That's the Q of the robot. Okay, but more generally, the real control problem, the big control problem, is acknowledging that the degrees of freedom in the problem are not just the degrees of freedom of the robot, but they're also the degrees of freedom from the environment, of the if I have a very simple problem here, right, my robot picking up a red brick, then the quaternion plus translation that describes the pose of the brick is part of my Q vector. And the control problem in its full glory is about regulating not just tracking a trajectory is great. Talking about force control, still relevant, but we have to find ways to do it on the whole Q, not just the state of the robot. Okay? And unfortunately, and maybe surprisingly, I think it takes time to sort of fully appreciate how baked in the assumptions are in those results that we talked about the fact that we're only controlling the degrees of freedom of the robot. Like those very strong results really relied on that assumption in a very specific way. So if you were to write, you can actually still write those exact same equations down if you have the full state of the robot. If you include Q to be the state of the brick and the state of the robot, they're almost exactly the same, right? I still have a mass matrix. My simulator is still thinking about masses, right? It's still thinking about, there's still a Coriolis term, right? There's still a gravity vector. All of those are true. There's one difference that comes in. Okay? And it's just this guy right here, okay? There's a matrix that has to go in front of the U, okay? And in general, when you have something like this, this matrix is going to be low rank. What does that mean? Okay, so basically, you don't have enough actuators. You don't have actuators on the brick directly. Okay, so U tends to be, the dimension of U tends to be strictly smaller than the dimension of Q. You don't have actuators on the brick, right? Now, there's a name for that, right? When this happens, that's called the system being underactuated. And I care enough about that that I have a whole other course about how to solve that, okay? It completely changes the control problem, okay? We'll dabble in it in the next few lectures. We'll dabble at some solutions for that. But it's a small change, but it completely breaks our ability to solve the problems the way we were. The reason is, okay, if U is here, then you could basically instantaneously create an acceleration that you wanted. You could always find torques up to torque limits or something, okay? You could always find torques that would cause an instantaneous acceleration in the joint robots. Okay? Once you don't have that, then you have to, it's changes from solving an instantaneous problem, instantaneously I'm going to move the robot in a certain way, and now you have to solve a long-term decision-making problem. You have to use the limited control you have to affect change at time 1, different changes at time 10, different changes at time 30, and it becomes a long-term reinforcement learning, optimal control, planning, use your favorite word for it, problem. Okay? You can't make decisions instantaneously. Okay, so it becomes, I mean, there's many ways to approach it, but I think the dominant formalism is an optimal control problem. And reinforcement learning is a form of optimal control. Reinforcement learning is sort of the field of approximate optimal control, or a particular type of approximate optimal control. Okay, we also talked about perception. Okay, there's another thing that's challenging when you have these extra variables, right? The first thing that sort of breaks is the fact that you're underactuated. Okay, the second thing that breaks is that just like we don't have actuators that directly attached to Q, okay, we had actuators directly attached to these joints, but we also have sensors directly attached to these joints. Okay, so perception also gets harder. I might have to use my cameras. I might have to use my tactile sensors. I use some other suite of tools, not just immediate joint encoders, to estimate Q, right? And then even that, remember when we talked about perception, we talked about maybe it's not even enough to estimate Q, maybe you have to actually put a probability distribution over Q, right? Because there's uncertainty that manifests in very subtle ways, and summarizing the state of the world with a nominal configuration may not be sufficient to capture the task. Okay. All right. So there's big things that change when you try to go from the manipulator control to the control of controlling the environment. And we need more tools to do that. And we're going to do that over the next few lectures. So today we'll do sort of the imitation learning version of that. We'll do the reinforcement learning version of that. We'll do a model-based reinforcement learning version of that. Okay, we're going to walk through a handful of different ways to do that. And if you want the full gamut, then you can take underactuated in the other term, or some of you already have. Okay? All right, good. So one thing that is a direct mapping, I guess, all of the controllers that we wrote here took the form u equals pi of q dot, okay? So this was some control policy be it the equations we used to do trajectory tracking, the equations we used to do force control, the equations we used to do impedance control. Okay, they were all a function that took in q dot, possibly the desired, and output the torques. Okay. Now we're going to generalize this, but we're going to still bake in sort of this notion of a policy. Okay. So today we're going to think about possibly extending this to, you know, can I call that just pi of x, since we know x is q dot, right? So we're going to do this. We're going to think about what it looks like to do this, where x is the, you know, q robot, q environment, q dot robot, the whole thing. Okay, but we're also going to try to write controllers of a slightly different form, where maybe we want to have a direct mapping from, let's say, cameras or sensors, you know, tactile, you name it, into our control actions. Okay. One way to do that is to write an estimator that takes those sensors and approximates x hat, and then write controllers of this form. Okay? That's a very appealing way to do that, because then we get to use all of our math, all of our structured equations, okay, and a lot of things go through. And I would say this has been the dominant way that people have been trying to control robots for many, many years. Okay? But we got a little stuck. I mean, we got a little bit stuck in it. I think there's still a lot more to do here. Okay? But I do think that this assumption or this requirement of trying to estimate as a first step, estimating the state of the world, and then as a second step, trying to apply the controller given a known or an estimated state of the world, I think we kind of, most of us would agree that that was maybe not the best way to go, right? We can do better than that. And this came up when we talked about perception, right? We said there's an explicit choice. You can try to do pose estimation directly from perception, but sometimes you can do less and still get the job done. So we talked about estimating just key points, and that's enough to move objects around pretty much. You know, maybe you can just estimate dense descriptors, right? There are weaker forms of things you can estimate that still allow you to make really good control decisions. And then the burden of estimating this well, first of all, it's not sufficient. In general, you need a probability distribution over x. And second of all, it's actually a lot to ask to come up with a canonical definition of x. Okay, so take that as it is, okay? Now ask the question, what if we wanted to, you know, reason about these equations, but we want to do it, remember this example from last time? We want to do it, write a single controller that works over an entire class of objects, right? So this was just the example from the key point and the category level, right? So you want to write one controller that works for all of the mugs. I haven't captured that in any of these equations yet, right? Somehow that would say I want a single pi that works for many different instantiations of this set of equations. One can capture that, okay? But that's a new object to think about. It's not just about reasoning about this one set of equations, it's reasoning about an entire distribution over those equations, where those subtleties of those distribution, they come in the contact geometry, and they come in the mass matrices and all this. How do you write a single controller that works for all of those? Okay, that's tough. But for me, the one that really broke sort of broke everything, right, is when I started thinking about tasks like this, okay? Because I really like these equations, okay? But if you ask me to write down Q and and someone's chopping an onion, just think about like, okay, the number of bodies is changing dramatically every time. Even if I want to simulate, it's kind of a pain to simulate that, right? I think that just kind of breaks this approach, right? Estimating the pose, even the number of all the pieces of the onion as the first step in sort of making a control decision just doesn't fly, okay? Now, ironically, I think I spent years trying to convince people that you shouldn't do this for legged robots, okay? And nobody knew what I was talking about, because you could always build a better state estimator, okay? And that's part of the reason I switched to manipulation, was because I started showing videos like this, and people were like, oh yeah, of course you wouldn't want to estimate X for that, right? But I think it's also true for quadrupeds and the like, and I think some of the RL success that we've seen is partly showing that that's been true. Here's a couple other of my favorite examples. So, I still don't have a robot that does this wonderfully. But think about like what X is, right, for that. Okay? Think about writing a controller that first estimates the state of the shoelace. Probably it's some finite approximation of the infinite dimensional state of the deformable body, right? But that's just not the way I tie a shoelace. Like I don't estimate the full topology of my shoe in order to tie my laces, right? I'm doing something much more simple, much more local, probably, using my touch sensors. When it goes wrong, I normally just like yank it and start over, because it's really hard to fix a knot if it goes wrong, right? We haven't captured that in any of these equations yet. I always talked about spreading peanut butter on toast. Like, it sounds like such a simple thing. I didn't do it this morning, but I could have done this morning for my kid, and that just breaks all the equations. Like, it just breaks the equations. I don't even know how an efficient way to represent that. One more of my favorite examples, buttoning your shirt, okay? The state estimation view of the world, which again, robotics was all about this for a very, very long time. But the state estimation view of the world would sort of be, step one is estimate the full state of my shirt, right? But this one to me just feels so obviously very local. Like I'm feeling roughly the orientation of the button in my finger. I'm feeling sort of where it is I'm not estimating like the back of my shirt, right? That's too much to ask, is to fully estimate the state of the world in order to make your first control decision. Okay, so how do we do it? So like I said, we're gonna show you a number of ways to try to build these more interesting controllers. But I think one of the great things that's happened in the sort of the learning revolution as it came into robotics is that people they just broke out of this mold a bit, okay? And one of the first things there's been the ordering is a little bit complicated, okay? But one of the things that happened is, okay, can we just do learning for that? In the simplest form of that would be to say, we've talked about all the ways it's complicated, but actually humans make this look really easy. So around the time when people started getting excited about VR and AR headsets again, okay, the roboticists started saying, okay, I can actually make some pretty useful teleop interfaces, right? So people made this is the PR2, okay? You've seen versions that are HTC Vive kind of things. You've seen people that have Zoe actually has some sort of plastic fingers in here to like a teleop device, okay? And some of the best videos you've seen of robots doing incredible things had a human on the other side using one of these great VR teleop devices, okay? Yeah, so she's got little grippers and claws. And the PR2 made a splash, actually, because that first video, which I showed in the first lecture, of the PR2 going in and doing all the things you might want a robot to do in the house, it was teleoperated, but it's extremely capable. Okay? There was a recent competition, actually, in one of the X Prize competitions. It's called the Avatar X Prize. And it was roughly a a teleop robot competition. Can you make a robot that could do all the things with a remote teleop and make it was actually also, you didn't get to supply the pilot. The judges were the pilots, and they had to don your system, and it had to be usable enough that it could go through a series of challenges, and you could communicate with another human through the robot. You could diffuse a bomb or open a, there was a handful of things that they did. But this actually, again, pushed the technology pretty dramatically. So this was one of the winning, Nimbra was the winning competition. That's actually Jerry Pratt, who was the pilot that day. He was one of the judges. And I believe this is the winning run, because Jerry was the winning pilot on the winning run of that competition. Okay? But they started developing like really nice teleop interfaces, doing highly non-trivial things with their robots. Okay, another one of the entries in that competition was done by Northeastern. This is Peter Whitney's group at Northeastern. I got to go over and play with this one. It's super cool. Okay. Fairly dexterous. You could basically just, you could just put on the robot, feel the, put on these sort of haptic gloves, put on the headset. You can be in the other room, and you can do amazing things, right? So there's something like there's like a disconnect between saying how hard the problem is in this way, and then how easy it is when you just let a human go on the other side, and they can do most of the things we care about. That's what the device looks like, yeah? This one, some of them have haptic feedback, right? So this one, you can actually feel the forces that the robot is feeling. Yeah? So to some extent, we've been able to teleop for a really long time. Like there have been teleop interfaces to robots for many, many years. I think the robots, we now have smaller robots that have force control and can give haptic interface back. So I think the robots have just gotten better. But we've known how to teleop for a long time. I also think that VR got better, right? So people have more and more immersive interfaces. And there's continued research on that to make that even better. So if we wanted to, we could bring the robot future maybe by just having enough people wearing enough goggles, okay? But the hope is maybe that we can capture what's happening through this interface, do some learning, and turn that into a controller that we can use and the human can go home, yeah? So the great thing about having these interfaces is that control becomes a supervised learning problem. Right? So now, if we have a setting where the human can do all the tasks that we care about, and there's cameras, tactile sensors coming in, right? And you're feeling haptic feedback, for instance, right? Tactile or force sensing in, and they're making robot commands come out. Okay, then it becomes seemingly, tantalizingly appealing way to think about this would be to say, if I do the same sensors coming in, and I want to learn my robot controller and send the robot commands out, then that could be with supervised learning. So I could just put a neural network in here, for instance, okay, that takes the sensors, outputs the command. In general, it's a sequence learning problem. Okay, Okay, for the same reasons we talked about a minute ago, that you might have you might not be able to just look at the instantaneous sensor readings and inform yourself everything about the world. You might not be able to take a single instantaneous command in order to accomplish an advanced task. In general, you have a sequence of sensor observations and a sequence of robot commands that are implied by that. Okay, so it's potentially a recurrent neural network in here, or you have a history of observations. Okay, we'll talk a little bit about the different versions of that in a second. Okay, so this is like the simplest type of control in some sense. We're just going to copy the human. And it's powerful. I mean, I think the major limitation, people would say, the first thing you'd say is, first of all, there's a burden of giving human demonstrations. Okay. The second thing people say is that the performance of your robot could be limited by the performance of a human. And we'd like to have superhuman robots, right? Now, that's actually a subtle argument. It is possible to do imitation learning in a way where the imitator surpasses the performance of the human. That's actually not a glass ceiling immediately. Okay, that's one of the core results in sort of supervised learning of this type. But it's, you know, okay, but you're not going to do something that a human never did, probably. Okay, but you might track trajectories better or other things. Yes. There are many ways that it could happen. I think the immediate sort of claim in the original behavior cloning papers was more about humans might give noisy demonstrations and you would learn a beautiful manifold of solutions, okay, that could be, you could interpolate better than any independent sort of output of a human. Okay, but there are other subtle ways like bandwidth and other things that could be involved. Yeah. Okay, so the question is how transferable, right? So we'll start by just talking about the robot. The human is demonstrating exactly on the robot and exactly the task that you're trying to demonstrate. But this is, a few of us were talking about this as people were walking in. Okay, but the quest that a lot of people are on, I would put myself amongst them, is maybe if you do this enough and you learn enough skills from enough humans, then you can have your ChatGPT moment. And have generalization, possibly to new robots, but certainly to new tasks in a zero-shot or prompting kind of way. So I think it's an open question. I think the true believers would say that you could, again, do more than you've seen by learning enough behaviors, having a large enough capacity model that it learned something fundamental about the physics and of interaction and could do something brand new, right? I would count myself among the believers. GPT is a pretty amazing thing. Okay, so how do we do that? So generally speaking, this becomes the stuff of imitation learning. And more specifically, this is behavior cloning, okay? So I would say there's two dominant approaches to imitation learning. The one we'll talk about today, and the one I've been leading up to here, is behavior cloning, where we're really trying to mimic the input-output, input-output from human. Okay. There's another form that is popular. I'd say behavior cloning is on fire today because it's working so well. But the other one that's very popular is you could call it. I'll call it inverse optimal control. If you went to a conference today and you called it inverse optimal control, everybody would look at you funny. They would call it inverse reinforcement learning. Okay, but there's a slightly different version of this where instead of trying to learn directly the input-output mapping from the human, what you really want to learn from the human is the reward function, and then solve the control problem against that reward function. Okay, but the setup I gave you here is really about behavior cloning, so we'll stick to that. Yeah? Those are slightly different. I would say implicit behavior cloning is still behavior cloning. No. Implicit behavior cloning does not. I thought about talking about that. I don't think I'll talk about it, but yeah, so it uses energy, sort of an energy based model, okay, but it doesn't have an interpretation directly as a Q function. There's no cost function required for implicit behavior cloning. Yeah? Yes? Okay, yeah, good. So does this help with like peanut butter and shirts, right? So how could this potentially help? So if I'm doing this as a sort of sequence learning, and maybe I'll make the point in just a minute, okay? So the internal architecture here, if it's just a big neural network, for instance, okay, there is no explicit requirement here in the middle to try to first estimate the state of the shirt. If I learn a more direct mapping from sensors, whatever is required inside here to learn the mapping from sensors to torque, what we hope is that learning is going to find the sufficient representation, which is sort of maybe a more minimal, it might not be minimal in the dimensionality sense, but it will be more targeted representation that focuses the attention of the representation on the relevant parts of the task, right? So that's putting faith in the learning algorithm, but it's certainly not constrained to do the thing of estimating the full state. So that's why it's fundamentally different. Okay, yeah, so and I guess that's actually a perfect transition. So, here's one more cool teleop that started up. This is actually Aloha, which is from Stanford, and it's I think it's good for many reasons, but one of them is that it's low cost. So some of the systems I showed you that have kind of haptic interfaces are pretty expensive. This one is low cost, surprisingly low cost arms doing surprisingly dexterous tasks. Some of you were at Coral and maybe got to play with it. Anybody play with it at Coral? Yeah, cool. Did you like it? Was it pretty effective? Yeah. So after I said something about tying shoelaces, and then I think like all my students were trying to tie shoelaces with it, and I don't think they quite managed. But my job is safe for another year. Okay, so yeah, here's the point that we were just talking about. Okay, so what is the architecture behind this? Oftentimes, this is sort of like the way they started in 2016. The first people that were trying to use sort of deep representations in that control layer. Oftentimes, they are, let's say, a big network, like a ResNet, like we were pre-trained on ImageNet, for instance. Okay. And then you have a relatively smaller control network. These tend to be sort of surprisingly small, a few layers, a few hundred units in the middle, 255, 255, 255 kind of thing, okay? But the essential point here is that when we were doing perception before, we were always saying that the output of this, in order to put it into our classic control, needed to be somehow interpretable, right? We chose key points because I could write a controller that took key points and made decisions based on that. I chose pose because I could reason about that directly. And here, there's no explicit, there's a map for all the way from pixels to torques, if you will. Probably not torques. Probably this is still going to go into a low-level manipulator control. Okay, but the cheeky word for it is pixels to torque. All right, and the middle is not required to be an interpretable representation. And I think that's just such a big deal. That really breaks free into a different class of representations, which are learned from data. They are sufficient to accomplish the task, and they need not be interpretable. It removes a big burden. Okay. So in some sense, remember we said one of the successes of deep learning, maybe one of the biggest successes of deep learning, was that you could like train on ImageNet. That was where the task was object recognition. And if you cared about, you didn't care about elephants, you cared about dishes and spoons, then you just drop the final layer off, put on a new layer, and just fine tune with a little bit of data to get an object detection for plates and spoons, right? In some sense, the proposal here, pre-train on ImageNet, or we could use other, the self-supervised, we could use Dino V2, we could do whatever our sort of pre-trained thing. And to some extent, control is just fine-tuning, right? It makes me very sad to say that. But just think about it that way for a minute, right? You're going to lop the last layer off your pre-trained ImageNet. You're going to put a relatively small head on it, okay? And you're going to fine-tune that to solve the control task. It's kind of amazing that we could potentially do that, okay? And it works better than it should. Okay, I started playing with this. So people were, Sergey and Chelsea and others were doing it starting in 2016. I'd say we started more in earnest in 2018 in my lab. This is Pete Florence, Lucas Manueli, and Yunzu were working on this too. Okay, but they started trying to take the dense descriptors that we learned about last time and saying, what if we used dense descriptors for that Z and close this visual motor learning with sort of imitation learning? Okay, and the results that came out of that really were deeply influential for me. The controls were robust in ways that I had not seen controllers be robust before. I think basically because they were closing a loop on the RGB sensors directly. And we never had high rate feedback control based on cameras before that. And seeing that work and seeing you could just shove things around and it had a very robust response was deeply influential in the way I thought about control. Okay? So let me tell you a little bit about how that works. Okay? So the idea there was we take that latent representation Z, which was arbitrary pre-trained feature. Oh, sorry, go ahead.
Sorry, in the network that you showed,
yeah.
Is it basically at this current frame of sensor inputs that I have, this is the current output, or is there like a time element?
Right. So the original image didn't actually have history. I wrote that in because you can see it's like a little different color. I should probably color match it a little better. Okay, because in general you can't just take the instantaneous image and expect to have a sufficient representation. Partly because of occlusions, right? It could be that if you opened the drawer, saw that there was something in it, closed the drawer, yeah, there's still something in the drawer. You can pretend there's not, but you should remember that, right? Or even if you just want to do anything that has a dependence on velocity, for instance, you might need multiple frames in order to estimate the velocity if that's part of your state. Yeah, so I think in general, you need a history or you need a recurrent network somewhere in here. Those are kind of your two options. Yeah, Jason. Yeah, so the simplest proposal would be, let's say I'm going to pre-train on ImageNet. I'm going to just take the second to last layer, I guess, lop off the one that's directly mapping to elephants and clowns or whatever, okay, and use that second to last layer as Z, okay. But we've gone a lot of exploration since then to think about what is the right representation to Z, what's the right way to pre-train these things. I think there's more work to do. Yeah. Yeah. So that's good. Okay, I will answer that specifically, but in a little bit. I've got a couple things that will build up to that. The question was, have we thought about using attention? So definitely, people are using transformers now to do that front end. So if you've seen like the Google RT1, RT2, or even just decision transformers before that, or there's a lot of work out there now trying to do transformers on the front end. Okay. Yeah. Good. So for instance, a different alternative than using the pre-trained ImageNet would be, what if we learned those dense descriptors? Could we use the dense descriptors as a particularly task-relevant choice of z. Okay? So the dense descriptors is like image in, descriptor, the size of the image out. Okay? So to be a little bit more efficient, what Pete and Lucas and company did was they would pick some small number of canonical points in the d-dimensional space, right, in that embedding space, and then they would actually run the correspondence. So basically, the same way the visualization in the dense descriptors, remember, was we put a mouse over one part of the hat, and then we tried to track that part of the hat. So imagine putting the mouse down on 15 random points in the hat, and you want to track those and use the positions of those as the z element. Okay, that's just a different proposal. I wouldn't say it's the it was maybe the winning one in 2018 or 2019. We've done lots of things that are sort of in this space now. Okay, but that's another way you could potentially come up with z, and that's the way that these guys did, which worked so well that it really changed my mind about things. Okay, so here's roughly how it worked. This is actually a very simple teleop interface. Pete would sit right in front of the robot, use the mouse and keyboard, okay, put the shoe, random shoe, in the relatively random orientation. You can also behavior clone from a simulation. I'll make another point about that in a minute, okay? But imagine just sitting there and doing that 200 times, let's say, okay? It's kind of a small cost if the thing you get out is awesome, right? But so in this case, this was just to make sure we understood the behavior cloning pipeline instead of having to do that every single time when we were debugging all the parameters and everything. Pete just wrote a simple controller in simulation, okay, and then just made that give demonstrations and made sure that they could clone the existing controller into a neural network controller. Just kind of shake the cobwebs out, okay? Now that has turned out to be an extremely useful thing to do. So even people who are doing some of the best work in reinforcement learning these days will often use privileged information in reinforcement learning first, and then do behavior cloning to go from a privileged information controller into one that actually solves the sensors, the pixels to torques controllers. So this is, that left is actually kind of state of the art for RL. The general approach is state of the art for RL also. Okay. Now, in this case, the controller was not a history of observations. It was using a recurrent network, okay, and it was a small recurrent network, LSTM, about 100 hidden units, okay, and it was doing in simulation from simulated cameras some basic sort of box pushing, flip the box kind of tasks. All right, now here's maybe the essential point, and maybe to your point about when do these things work on, do they transfer to different robots or whatever. The mental model I still to this day have about these controllers is that you give a bunch of demonstrations, okay? And roughly speaking, this is a very hard thing to define. Pete worked really hard to make a plot that would show in 2D sort of the complexity of the task, okay? But roughly speaking, the tasks that were successful, this is task success in color, are, the rollouts that were successful were roughly in the convex hull of the demonstrations, okay? This is the same, this is not unique to behavior cloning, this is like machine learning in general, right? Interpolation works incredibly well, which means it's sort of inside the data, Extrapolation beyond the data tends to not work very well, okay? And the same thing is true here, but I think that's a useful mental model of how these things can work in practice. If you put in front of your behavior cloned policy something that it's never seen before, it won't probably accomplish the task. You'd have to get lucky. Now, the dream of foundation models, I guess, is that you get your data set big enough that basically everything is interpolation, right? That's what happens maybe with GPT. Okay. Yeah, so just, I really have to, I can't say enough how impressive this was to me, right? So, we've had robots, we've had humanoid robots doing cool things or whatever, but somehow this was just like, what? I can't believe this worked so well. So, picking up the plate, okay, but then I thought, well, surely it'll be, you'll be able to antagonize it with visual distractors, right? that you just you change the visual scene, the thing's going to completely fail. But I don't know, it was trained on ImageNet. It had features that were somehow robust to a lot of the visual. He didn't give demonstrations with all this stuff in it, right? But the rollouts were surprisingly robust to visual distractors. Okay. And really, I mean, if you could go in and antagonize that robot, and it would almost always get the job done. Now, this was sort of an early version of something that I thought I couldn't model very well. Like the hat, it's not super deformable, but it's deformable, right? The state of that is non-trivial to write down. And the task here was just always put the hat on the rack, okay? But there's no notion of estimating the state of the hat anywhere in this pipeline. And it can still do the task, right? Humans could do the task. Maybe that shouldn't be surprising, right? But you can teleop the task. Maybe you can play it back. This is 51 demonstrations. Like the things it's doing are not that complicated, but the ability to close the loop on the cameras is just so valuable. Okay, so it's actually kind of a trend, all right? So a few years ago, everybody was talking about our reinforcement learning, okay? People are still doing excellent work on reinforcement learning. There's lots of work to do, but it is maybe surprising how many people are excited about behavior cloning these days, right? There's really, these models are able to consume lots of demonstration data. People are willing to give lots of demonstration data, find ways to get it off YouTube, okay? And a lot of the best manipulation systems today, certainly in terms of demo quality, right, are actually coming out of these behavior cloning pipelines. Anybody disagree? I mean, you're welcome to disagree. Yeah, like it's surprisingly effective. Okay, so we actually did some work at TRI about this. This is kind of the new push that we've been doing there. I linked to the blog post if anybody wants, but I have to show you some of the results that have been coming out here. Okay, so because we spent so much time working on simulation and on model-based control, we decided to start working in TRI about, we've always picked challenge problems, and we basically said, let's focus on tasks that we cannot simulate, where the model-based control, the same thing I said here at the beginning, right? So I want to focus on the tasks that really estimating the state is a non-starter, right? So we started doing a lot of tasks with food, with deformable things, okay? And the new representation, which I'll come back and tell you a little bit of the details about, is using these diffusion models to represent the policy. So inside here is a thing that's doing diffusion. Maybe I'll tell you the story first, and then I'll tell you the technical details, okay? And it's funny, because I've been giving those examples at the beginning for years, and they went through and they basically did almost every one of my examples, to the point where they're like, yeah, I said, if you do the shoe tying, I'm going to have to retire, right? That's this is not actually peanut butter, it's chocolate hummus, but it's close, okay? Peeling potato, I used to say peeling potatoes too, I have to stop saying that. You know, turning pages on a book. These are pretty delicate things, okay? But they're working incredibly well, okay? It's things that I thought weren't going to be possible anytime soon. Take, 50 demonstrations, a few hours on the GPU to train, okay? And then like really good things are rolling out the back in the convex hull of the training data, okay? They still have that sort of visuomotor robustness, right? So you can antagonize these things. This was beating an egg, okay? We didn't have the egg in that particular antagonizing video, but normally you can actually beat the eggs, okay? This is a good example because it's actually an example where at the low level, you actually need force control to do that task, right? So if the human doesn't feel the forces, then it's very, very hard to do that task. I sent it to Neville, that particular video, yeah. And then you remember I talked a lot about the dish loading project, okay? So Naveen one day just said, oh, I'm going to go ahead and try to do dish loading with this new behavior cloning stuff. And basically in 3 hours, he did what took us 3 years to do previously, and it's pretty darn good. This is a surprisingly, like in the sequence learning sense, you might worry about tasks that have really long duration. This is a pretty long duration task, and it's being captured in these big models. Yeah.
I noticed this one has the spongy visual
Yeah.
tactile thing. Did all the others also have a lot of tactile sensing?
Yep. So not all the others. So the egg beater, for instance, the bimanual setup doesn't. There are some tasks that really benefit from the tactile sensing, and I'll show the video of that in a second. But there's some tasks that really benefit from that, others that it's not so big. So there's two things. Let's separate. So in one case, there's a different sets of inputs for the human. So there's one question is, does the human feel the forces? Okay. The egg beater, the human needed to feel the forces, but that was using the joint torque sensing and relaying that back to a haptic teleop interface. Okay. There's another thing, which is, does the robot always feels the joint torque sensors, but this one, when they have the bubble thing on there, then they optionally get a higher resolution force and geometry sensing at the interface. And that gives additional sort of tactile information to the robot for the controller. Yeah.
Direct output from the bubble to the model, or did you feed the like?
Yeah. It was the image, another image in. Yeah. Sorry, one more here first. It's we're recording everything that the robot sees. So it's the cameras. It's typically multiple cameras. A camera. There's even a camera in that bubble, for instance. Okay. The joint torques, the joint positions. We're sending all that. That's a big log, and we're going to send all of that through the robot. Yeah. Okay. No, Naveen teleoped 50 to 100 times that task. Yeah. We now have so I think one of the big things that's happened with the diffusion sort of version, which I'll tell you that story, is that it used to be that a lot of the behavior cloning demos required expert demonstrations, and they just barely worked. But we've gotten to the point where now it's much easier to give the demonstrations and get good results out for some subtle reasons that you'll see in a minute. But yeah, I think anybody who's willing to sort of do that demonstration, that one was actually with a space mouse. So patient guy, yeah.
Just as a follow-up to this, I was surprised that the 200 data point that you of this, I think that they're sufficient to, I guess maybe that was exactly the surprise you were talking about, but I was just surprised that like 200 points are enough.
So just to be clear, so it's like, yeah, let's say 50 to 100 demonstrations. It depends. I mean, 50 tends to be enough to get the nominal behavior. If we really want to get the kinks out, then we try to show more recovery kind of behaviors. Okay, and you get up to 100, maybe even 200 if you're really trying to be careful. But yes, so and they're temporally extended. So it's actually a lot of data, right? Because you're getting like a video at frame rate over multiple seconds for each of that data. Okay, but they're pretty high capacity models with 150 million parameters in there. So it is surprising that little amount of data gives that robust performance. I agree with you. Is that a feature or bug? So he says the robot's a little discretized. It's probably not a feature. You're saying this one here? Oh yeah, this one here, I think it does. So it's true that the Visuomotor loop is only closed. Yeah, I see that. That goes a little bit like this, yeah. So that could be maybe not training it and not letting the model train long enough, right? And not the human demonstrations. It could be that there's a bunch of things that could explain that. Normally, we definitely see some very, very smooth motions. You can occasionally see that kind of behavior. It's probably an artifact in the learned policy. Yeah. The controller is capable of beautiful smooth motions, the low-level controller. Like the output here is not torques. It goes through an operation space controller, and that is, the human demonstrations are beautiful and clean. Yeah? Okay, so the same, you probably wouldn't use this to bake a cake. I don't know. It's possible you could use this to bake a cake. Here's how, okay? My 3-step plan. No, so the versions I'm talking about so far are trained one skill at a time, okay? The bigger versions of this are trained on many skills, and they are conditioned on the goal of the skill. It gets exciting when that conditioning is language conditioning. Suddenly you've connected yourself to an LLM, okay? And now the reasoning power of the LLM becomes available in some sense to your controller. So if I ask GPT to give me step-by-step instructions to bake a cake, and each of those can directly be fed into these controllers because they can be conditioned on language, you might just get a cake, right? It might not be delicious, but we've seen pizzas come out that look pretty funny. But it's the start of something pretty that I didn't know how to do before. Yeah. Cool. So yeah, I mean the cool thing is that this is, so now we're like just trying to see how we're going to try to build many skills. And so like all the time. So some of you came and visited. The Graduate Women in Robotics group came and visited just the other day, and we showed this sort of demo. But basically every day there's new skills. We actually now have a full-time robot demonstrator. It's a job, right? It's a great job, actually. You know, and so it's like try to come up with something that you can do with 2 hands that involves some props. Ideally, my favorite ones are the ones that don't involve rigid objects, right? And be patient enough to get 50 to 100 demonstrations. Let the GPU train overnight, and then you come back the next day and you see this kind of thing coming out. Okay, let me tell you a little bit about, oh, go ahead, yeah.
Just quickly, how do you do the training? You were saying like there's a mouse.
There's a couple different interfaces, and I think we're still revving on that. The simplest one, the one we started a lot with, was just a space mouse. I don't know if you've ever seen these space mouse. I could bring one in. They look like a little hockey puck kind of thing, and it's a 3D mouse, basically. You can XYZ, and then you can also click the button and then do yaw pitch roll. And it tends to give sort of rectilinear motions, okay, out, but a capable operator is very capable with a space mouse. They were meant for CAD initially. But then there's also, I'll show you the video of the human demonstration for the bimanual is actually a big bimanual haptic feedback device, which looks more like a robot you're hooked up to. Yeah. Yep. Yeah, increasingly people are excited about that. What's the name of the new Meta thing where you can have huge monitors, right? That's pretty good hand tracking. I wouldn't be surprised if people start doing it. I mean, you won't get the haptics that way immediately, but there's new work out of CMU just the other day that has like gloves that have actuators inside. Like the stuff's happening so fast, it's incredible. So I would not be surprised if we're all wearing VR goggles and teleoping robots soon. Yeah. Okay, so the particular architecture that's inside here is based on these diffusion models. How many people have seen diffusion? I mean, you might have used stable diffusion to generate cool images, right? Or DALL-E, right? So okay, so how do you make that work for a robot? Okay. First of all, the basic thing to know about diffusion is it's another idea about self-supervised learning. Okay. If you want to generate a bunch of random images, right? You don't want to have humans label things. Then a basic thing to do, which turns out to be incredibly clever, okay, incredibly effective. Take any image from your data set, start corrupting it by noise. Okay, that's one of the transformations you could do to images. Just take random noise, random Gaussian noise, and add it to the image. Okay, and then use that transition from an image to random noise to train the backwards process. So if you want to get a new image out, you can start with random noise, okay, and then run it through the network this way and get something. It's mind-blowing that you get something that looks like like DALL-E or Stable Diffusion out, but that's what's happening. Okay, so we've been trying lots of things. We tried a lot of implicit behavior cloning kind of ideas. Okay, But this is what started working really well for the robots. Yeah. So the way I like to think about diffusion is actually, so Frank and Chen-Yang have been working on sort of a deterministic, simpler maybe version of this. I coded up a diffusion example notebook. I spent way too much time on it this morning. All right, so it's kind of in the notes now. I'll send some hyperparameters after class. Okay, here's my simple example. I think sort of the manifold hypothesis for denoising diffusion is that maybe the images that you are experiencing on the web, even though they live in this super high dimensional pixel space, actually the natural images live on some lower dimensional manifold. Okay? So to sort of play with that, here's a trajectory in 2 dimensions. Okay, I just made a Bezier curve that was not, that was slightly interesting in 2 dimensions. And then what we're going to do is we're going to learn a denoiser from that trajectory, to get back to that manifold. Okay, so think about every point on this as being maybe an image, and I'm going to add noise to it, and then I'm going to generate new points on the manifold by picking a random point here, and then running my denoiser to get back to it. Okay, and the code is actually very simple to do this. It requires, I hate hyperparameter tuning. I hate it. I'm completely allergic. At TRI, they hyperparameter tuned once, and they've locked that in, and we don't hyperparameter tune anymore, which is one of the reasons that I like the diffusion policies. Okay, but I had to hyperparameter tune for this morning, and okay, so the code is sort of, I'm going to pick a bunch of random points on that manifold. Okay, I'm going to generate random noise that's uniform variance noise in the same dimension as my image, or in this case in my trajectory. And then I'm going to add various amounts of noise to it. Okay, and I run my little learning curve. Okay, and the thing you get out is a denoising function. Okay, so for any one level of noise that you put in, if you were to plot the denoising step that it would take, then it looks like a vector field that's pushing you back onto the manifold. Okay, and the fact that this picture, I think this is the mental image that people use, or at least I use when I think even about stable diffusion for images. But it's crazy that works, right? Crazy that works. And somehow it seems to be a better representation for learning in some ways. It's learning extremely high dimensional continuous outputs, right? And the learning curves are pretty good. The loss functions are, the training is stable. And then this is kind of what it looks like to do the denoising. You pick a random point, which in the image case is a random image. Okay, in this case it's just a random point in 2D, and then I run my reverse diffusion, my denoising, and it finds its way back to the manifold. Okay, if I ran this a little longer, I think I could get more exactly back on the manifold, but this is just a very simple example with a multi-layer perceptron that's 255 units. Okay, you can play with it if you like. If you get better hyperparameters, let me know. I might stop. Okay, but the idea is clear, I think. Or helps me make the idea clear in my head. Okay. Now, how do I do that for a robot? Okay, what's the picture? So that's sort of a picture of diffusion in general. How does it work for a robot? Let me go out of order here. Okay, so here's a simple, interesting task where the state of the task is the state of the robot plus the state of the T, and you're trying to push it into a known state. So this could be described with a canonical sort of controls framework. Okay, so now the denoising is going to come up with a trajectory for the robot. So conditioned on the image, it's going to try to denoise to a set of actions for the robot. So it looks like this. It takes random noise, a random possible trajectory, and it does that same denoising to come down into a coherent set of actions that were conditioned on a small history of observations. That's the architecture, okay? So this is going to the questions about history of observations versus RNNs or whatever. So the way this is set up, it's a dynamical system, right? So it's a control policy. It's a sequence learner, if you will. It has a sequence coming in, a sequence going out, and it's set up to be an autoregressive model. So in the language of dynamical systems, if you wanted to implement this as a system in Drake, it's an autoregressive model where it takes the history of observations and actually also its actions. The interesting thing is it's actually predicting a sequence of future actions. So the policy that I wrote over there just takes maybe a history of observations and then predicts the next action. And then you run the history of observations, you predict the next action, okay? This is actually predicting many actions into the future for a very subtle reason. Like, it doesn't work as well if you don't do that. That was a double negative. It works better if you do that, okay? Okay, for very subtle reasons. So the architecture is, doing this sort of the denoising diffusion. Takes a small history of observations, predicts those actions. It's a big old pre-trained on, it's the perception head is pre-trained on ImageNet, okay? A lot of the denoising diffusion, like in stable baselines and the like, are using UNets for the bottom half. We are using them also here. I don't know if that's fundamental or not. I think it's fundamental in some of the success in images. I'm not sure if it's fundamental here yet. Okay, these are big models, but they're actually small compared. They get a lot bigger when you start conditioning on language and other things. This is one thing I don't like. Like, every time you train, you have to, contribute, pay your tax, right? It's expensive to train these things. Okay. So why diffusion compared to all these other? So we could have just learned a feed-forward neural network. Why did we go through the problem of learning this distribution? It's because human demonstrations tend to be multimodal. And the T example was picked to try to show that, okay? There's like an obvious symmetry where if your robot point finger is here and you need to somehow push this way, then half the time the human might go this way, half of the time the human might go this way. But if you try to learn a function that goes from the current image to action, then the neural network might just go straight up the middle. Okay, so you need to learn a distribution over actions, not a single action. Okay, so that's how you get towards diffusion. So implicit behavior cloning is also trying to learn a distribution over actions. The RT2 transformer a lot of the transformer, you can use transformers with diffusion. It just happens that the people that are pushed the transformers the most are using categorical distributions to learn multimodal actions. Okay, there's many ways you can do it, but diffusion does it very naturally. I could have made, and intended to actually make just 2 of those trajectories, and then the denoising diffuser would go to either one, depending on where you sampled randomly in the image, right? If I had done that exact same experiment, but I said my manifold looked like this, okay? Then the random samples, the rollouts might have looked like this would converge here, this would converge here, this would, depending on the data, would. Okay, so it's capable of having different, different outcomes from the same input. Okay, and it wasn't until we got that right that we started seeing really robust performance. And the difference between an expert demonstrator, okay, and a general, letting anybody give demonstrations, this was a big difference. So in the T pushing, the symmetry and the multimodality was like staring us in the face. We chose this example to tell that story, okay? But it's happening all the time, all over the place. People would much more subtle ways it's happening in all the other cases. And so the expert demonstrators would be the ones that would really think hard about doing it exactly the same way every time to avoid multimodality. And once we switched to diffusion, we stopped worrying about that so much, okay? Made a big difference. It's actually very subtle. So I won't get into the math about it, okay? But one of the things people know about behavior cloning is that you need to have some notion of stability. We talked about it a little bit once before, okay? So if you're doing imitation learning and your system, the closed loop system, is not stable, then you tend to walk away from your data, okay? So if I have trajectories that roll out and are unstable, then I'll quickly move away from my demonstration data. I go out of my convex hull, and things get bad very fast, okay? So it's kind of well known that you need to have some sense of stability in order to do effective behavior cloning or imitation learning more generally, okay? But we also said we need to be able to do multimodal demonstrations. So there's some subtle things happening in this forecasting approach, okay, which allows you to sort of do both. You can be stable. Normally you would think that if you're stable, you wouldn't be able to split. But predicting coherent trajectories forward in time gives you the richness to be able to both go left or right, but also have stability. That's one of the arguments for why we needed the forecasting. Okay, so Andy's one of my favorite guys. He does incredibly good work. He gave a talk here last year, and he was talking about behavior cloning. And it really was, I think, true that you really need to collect your own expert data and don't trust anyone else to do the data. You know, avoid no action so your policy doesn't just sit there. Okay, collect lots and lots of data until extrapolation becomes interpolation, and train and test on the same day because your setup might change tomorrow. That's where we were at last year too, but it's really gotten a lot better. The diffusion policy version of it is dramatically more robust. Right, so I put up my list here, but there's a bunch of reasons why diffusion seems to be working well, but surprisingly small number of demonstrations, right? They handle multimodality. I like the continuous outputs. I like that it's based on math, right? There's like solid mathematical foundations. But I wouldn't say that it's the exclusive choice. I wouldn't say it's the only way you can make these things work. I think these are the Google transformer, robot transformer architectures, RT1 and RT2, that have been generating a lot of press lately. I think they can work too, right? RT1 and RT2 are farther along in terms of collecting diverse data on different objects and even different robots. They're doing more pick-and-place type tasks. TRI's niche has been to do much more dexterous tasks, right? More complicated manipulation. We're doing it, on less robots so far. All right, so let me just show so here's that haptic interface. So this is Eric. These are called haptions. They have like bike handles for user interface. You got to drive it just yesterday. But that, Eric gets to feel the forces that the Panda feels, and that makes all the difference for being able to do that constrained motion demonstration. But these are not low cost, unfortunately. They are expensive. All the control we did, the manipulator control, was essential to make this work. Okay, so this has got all the best, controllers implemented very well. So in the setting where we know where the table is, right, then there's guardrails that says don't let the human demonstrator slam the robot into the table. Someone told me the other day that you can tell, so that's self-collision avoidance, which is pretty subtle to get right on a bimanual setup. You have to make sure your robots are synchronized very well in addition to knowing their state. Someone said to me the other day, Kevin said to me the other day that you can tell it must be working well because the robot's not scuffed up, right? If you look at a robot demonstration like this, a bimanual one, if it's got scuff marks all over, then okay. But that makes a huge difference to making these things work. Here's the bubble sensor, right? So there's a camera inside those bubbles, and there's actually it's textured on the inside so that you can see you can use the camera to detect shear forces in addition to penetration, which would be the normal forces. And there are some tasks where that's really useful. That extra resolution that you get of having not only a higher resolution sensor, but right at the point of interface with a tool or something like that. The one that we talked about in the blog post was actually when you're using a spatula to flip pancakes, okay? And then someone comes in and moves the table down, right? It's interesting. The nominal one that doesn't use the bubble sensor will just kind of sit there and try to flip pancakes and just be a airball over the pancakes all day long, right? But the one that used the bubble sensor learned a controller that actually went down until it touched and then moved forward. So then you can move the table down, and it was robust to that perturbation in ways that the original one was not. That's just one example, right? Yeah, so this is an exciting time, right? So everybody's trying to scale these models. Some people are trying to pool data. Some people are trying to watch YouTube, whatever. We're trying to give lots of demonstrations on lots of high quality demonstrations and complex tasks, and see if something exciting pops out the back end, right? Where we ask it to do a task it's never done before, and it's learned something fundamental hidden in that vector z to do a new task, right? So we talked about that as the language condition policies. I don't know how many tasks we're going to need. This is one of the biggest questions in the field, and I think it depends on how clean your data is. It depends on how high quality your demonstrations are. Depends on how diverse your robots are, right? There's lots of things that are going to affect the answer to that. But at Coral the other day, there was a question posed to a handful of us, do you think scaling is all we need? And I don't believe, I'm not only going to work on scaling, but I wouldn't bet against. I got a lot of negatives today. I'm impressed by how far you can get with just scaling. I think if you just take the tools we have, of course, some improvements are made, and you just keep doing this, the ceiling is very high. I don't see an immediate reason why that stops working. Yeah. I actually removed that line. I had that on my slide. Is maybe control becomes like vision or NLP. Maybe not, right? I won't stop trying to understand things, right? So maybe I must say the other thing I said, which was that I think there's a handful of truths about control theory, and some of them you can see better with models. GCS is my favorite way to see that right now. Okay, that's this year's tool. I can understand things in a much deeper way looking through the lens of GCS. But I can do things that I can't do with GCS with this tool. So my philosophy on life is to try to understand them both and push. And I think when we're all done, we're going to see a lot of connections between all of them. But this stuff's working well. It's pretty good. Okay, see you next time.